Dear students, in this lecture video we are going to discuss about how to solve the deformation and stress analysis in a cantilever beam when it is subjected to uniformly varying load, that is UVL, using ANSYS APDL page. Okay, so this is the given problem. Here a cantilever beam is subjected to a UVL throughout its entire span with a magnitude of 162.28 Newton per meter, and the beam is having a length of 4.267 meter, which is distributed along the x-axis. The cross section of the beam is given as 0.1 into 0.1 meter square. Okay, then the material of the beam is assumed to be steel, so the Young's modulus value E can be assumed to be 2 into 10 power 11 Newton per meter square. Okay, so how to solve this problem using ANSYS APDL? The step-by-step procedure to solve this problem in ANSYS APDL page we will discuss. Okay, so to subject the given beam with uniformly varying load and to model the entire case in ANSYS APDL page, at the initial stage itself we can subdivide the entire beam element into say 4 elements. Okay, so we can subdivide the entire element into convenient number of elements. For simplicity, I am going to solve the entire structure by considering 4 subdivided elements. Okay, so this is element 1, 2, 3 and 4. Okay, so the nodal points will be 1, 2, 3, 4 and 5. Okay, so the beam is distributed along the x-axis, so the length of each individual elements will be 4.267 divided by 4, which will be 1.067 meter. So if we consider the first point as the origin 0, 0, 0, then the second nodal point will be 1.067, 0, 0 along the x-axis. Then the second nodal point will be 2.134, 0, 0. Fourth nodal point will be 3.2, 0, 0. Then the fifth point will be 4.267, 0. Similarly, the uniformly varying load should be applied accordingly based on the elements. A uniformly varying load means for each unit length of the beam, the magnitude of the load will get varied in the order 162.28 Newton per meter. Okay, so for the total length of 4.267 meter, 162.28 Newton per meter load is applied. Okay, so for each individual element, for say the first element, which is having a length of 1.067 meter, so for 1.067 meter, if we calculate the variation in the UVL, then we will arrive at the result 40.58 Newton per meter. So the variation can be marked as from the rightmost end. Here the value of the uniformly varying load is 0 Newton per meter, and here, that is from the lowest position, the uniformly varying load, the load gets varied uniformly, and at this point we have calculated the value as 40.58 Newton per meter. Similarly, from the 0th position at the second nodal position from the fixed end, here we have noted this node as node number 3. So from the rightmost end, that is from 0th position, the distance is totally 2.134 meter. So for 2.134 meter, if we calculate the variation in the load, then the result will be 81.159 Newton per meter. So in this element, that is at element 3, at the ith nodal point, the magnitude of the uniformly varying load will be 81.159 Newton meter. The variation is from 40.58 Newton meter to 81.15 Newton meter. Okay. If we calculate the variation at this location using the same procedure, that is 162.28 divided by 4.267 into this length, that is from this position to this position, the variation should be calculated for the distance of 3.2 meter. This distance is 3.2 meter. So here if we calculate for 3.2 meter, the variation will be 121.7 Newton per meter. So uniformly it is varying. Okay. Then for the whole length, already the value has been mentioned in the problem, 162.28 Newton per meter. With the aid of nodes and elements, we can model this entire structural problem in ANSYS APDL page. Let us discuss the step-by-step procedure. So first we have to define the type of problem in the ANSYS APDL page. It is a structural problem. Then preprocessor element type, we have to add the element. So here we are considering a beam problem. So beam 2 node 188. Material properties, material models, we have considered the material of the beam, given beam as steel. So it is an isotropic material with the Young's modulus value as 2×10⁻11. So I am giving all the input values with the unit meter. So the Young's modulus value is also substituted in Newton per meter square unit. Poisson's ratio, we need not bother about this. Then sections, beam, common sections. So already I have described in the previous lecture videos of ANSYS APDL page. That is, the breadth of the actual beam structure under consideration should be given as height of the beam in APDL page. Similarly, the height, actual height of the height means thickness of the structure. Beam structure should be put as breadth. Okay, actually, like that only the program is already programmed in APDL page. So here there is no problem with the dimensions because both the breadth and height, that is thickness of the beam, are same as 0.1 into 0.1 meter square. So 0.1 meter square. Then we can model using nodes and elements in active CS. So the first nodal point is set at origin 0, 0, 0. The second nodal point, already we have discussed the Cartesian coordinates of the nodal points. So the second nodal point is set at 1.067 meter and y coordinate is 0, z coordinate is 0. Then the third nodal point 2.134 meter along x direction. Then the fourth nodal point is 3.2, 0, 0. Then the fifth nodal point is 4.267 meter. Okay. Now we can join these nodal points to create the elements auto numbered through nodes 1, 2, 2, 3, 3, 4 and 4, 5. Okay. Since the entire structure has been modeled with the aid of nodes and elements command, we need not to go for the meshing option. So meshing option is required for key points and lines option only. Okay, so here we need not bother about that. Now we can apply the deformation constraint as well as loading conditions. So go to solution, define loads, apply structural displacement on nodes. Okay, here the structure is fixed at its leftmost position in all the directions, so all DOF is arrested. Then to apply the uniformly varying load step by step from the rightmost extreme. Okay, rightla irundhu zero la irundhu start panni maximum loading condition is acting on the leftmost position. Okay, so pressure on beams. So first select the last element. Okay, the load key is 2 to define the direction of the uniformly varying load as minus y direction, negative y direction. So in the element 4,5 at the ith node, that is at the 4th node, the value of the uniformly varying load is 40.58 Newton per meter, and at the jth node 0. So right hand side la irundhu it is getting varied. So right hand side, that is jth node la, that value is 0, from which it is uniformly varying, and at the point of 4, that is the ith point of the last element, where that is 40.58 Newton meter. Okay, apply. Then choose the next element. Okay, load key is 2. So now at the considered element, at the ith node, the uniformly varying load's value is 81.59, and at the jth node 40.58. Next select the next element. So already we have calculated this uniformly varying load for the ith and jth nodes of all the elements. So now also the load key is 2. So for this element, the value at the ith position 121.7, and at the jth position 81.159 Newton per meter. So now at the last element, the value at the ith node is 162.28, and at the jth position 121.7 Newton per meter. So here we can see the value which have been set in the ANSYS APDL page. While we are considering the 4th element, the value of UVL at the ith node is 40.58 Newton meter, and at the jth node it is 0 Newton meter. And while we are considering the 3rd element, at the ith node the value is 81.159, and at the jth node 40.58. The corresponding UVL values for the ith node of this second element is 121.7, and at the jth position of the second element is 81.15 Newton meter. Okay, so likewise we have given the values in the ANSYS APDL page. So now we have modeled the entire structural problem. So now we can solve the problem to get the deformation and stress results. Solution is done. So to read the results, go to General Post Processor, Plot Results, Contour Plot, Nodal Solution, DOF Solution, Displacement Vector Sum. So this is the result. So the maximum deformation experienced by the given cantilever beam subjected to uniformly varying load is 0.00111 meter, that is 1.11 millimeter. Okay, so to read the stress results, go to element table, define table, add. So the sequence number for the bending stresses in ANSYS APDL page is SMISC 32 at the ith node and SMISC 37 at the jth node. So by sequence number SMISC 32 apply, then by sequence number SMISC 37. Okay, then to read the stress results, go to plot results, line element results, SMISC 32, SMISC 37. Okay, so this is the stress induced results. Okay, the values are obtained with the unit of Newton per meter square. Okay, so if you want to observe the values per element, then we have to go to list results, nodal solution, DOF solution, displacement vector sum. So at each nodal point, how the deformation is experienced, that values we can collect from this table.